So designers have adopted different design strategies based on similarities and dissimilarities between products. Each time we design, we don't have to start from scratch. I've designed X, I can use some of that when I design Y. So there are similarities between product design approaches, but there are some dissimilarities because there are differences between products, and one key difference is the life cycle of a product. Some products are used over a decade or more. Some are used once and thrown away, right? So as a case in point, if you look at this list, this is in your handout. If you look at the bottom of the list, you're looking at disposable consumer products like what? You have moist towelettes. It's a product that's used once and thrown away. There are other things like when you go to McDonald's, you get your Big Mac in a cardboard container, you eat it and you throw it away. Stouffer's frozen food or Amy's frozen food, right? It's one-time use. Its lifetime is not long. But a t-shirt or a shoe, maybe a couple of years, maybe. But your automobile, maybe it lasts a decade or more. So they have different life cycles, and so our approach would have to be different. Now I also want to point out to you that how products have become complex, right? They are. If you look at the early part of the century, last century, when we were looking at the musket and Springfield rifle, the product had maybe 10, at best 100 parts. By the time you get to Model T, you're getting into the thousands. And today, and this is not even up to date, you're looking at a 747, we are at what, 777s and beyond, a million parts. So designing is an incredibly challenging activity. Because there are differences in life cycle, designers have to design, they make different decisions in terms of material choice, in terms of durability, right? I mean, an automobile has to be more durable than the moist towelette because you don't intend for it to last long. You have to think about remanufacturing and about recycling. Material choice too, how much the material costs will have a bearing on the life cycle of the product. If the product is to last a long time, then you would choose a different grade of material than one that's used only once. So you can see it's incredibly complex. So the design community over the years have developed a lot of toolkits because there's so much stuff that you have to remember. It's not just the function, it's how easy it is to manufacture, how easy it is to market, life cycle, and so on and so forth. So they have these toolkits that helps them meaning teams of designers, and that's something also we need to talk about. During the days of Henry Ford and the Wright brothers, products were not that complicated. The Wright brothers' first plane is not what our F-16s or Boeing planes are. And so the two brothers had enough knowledge of design and manufacturing and financing. Likewise, Henry Ford's Model T is not what the Ford Motor Company's products are today. There are a lot more parts and a lot more electronics and sophistication. So one person cannot do it. Edison, Henry Ford, and the Wright brothers had enough know-how. Firstly, we are too specialized these days. And so no one person can design the entire automobile. So it's a team. So when you have a team, you got to keep things organized, and you need a checklist, and that's what these toolkits do. It helps you to work effectively together as a team coordinated and keeping track of the multiple things you should consider. Two such tools are called the Pugh selection matrix and the House of Quality. It's called QFD as well. So obviously it's not an abbreviation for House of Quality, right? QFD doesn't make sense. It stands for Quality Function Deployment. So that's QFD. So these are two tools that were primarily designed for product design, but they can also help us incorporate environmental considerations. See, typically design tools are designed to take into account functionality, but with some effort we can also help enable them to account for environmental considerations as well. Let's talk a little bit about more of these. We'll talk about the Pugh selection matrix first. So it was developed in the last century. So this process is used during design and development when we have multiple design concepts. Typically, engineering firms, to launch a product, they usually start off with 8, 10, 20 concepts. These are all ideas for the product that are competing with one another. Clearly, we can only make one of these. But if you start off only with 3, you may not have even one good product idea. Typically, we need to generate a lot of ideas so that we hopefully will have maybe a couple or at least one good idea. So in the beginning part, there are multiple concepts for product. The Pugh selection matrix is used to compare these in an objective and consistent fashion, and to ultimately come up with that one winner that we are going to make. So it has 2 parts. The first part is called screening. The second part is called scoring. Product screening, product scoring. So in screening, the first part is where we have 10 or 15 product concepts. I had to bring this number down to a manageable 3 or 4. First stage. In the second step, we have 4 fairly good competitors, and there I want to be a little more detailed and do a more thorough analysis to come up with that one final. It's like an interview, right? You have a job opening that 100 people apply. Well, you don't want to pour over all 100 applications in great detail. You don't have the time to do that. You want to look at your major required qualifications. Many people will just drop out because a lot of people apply without reading the description, right? So from 100, if it came down to 20 or 15, that's the screening part. Now the remaining 15 means they have many aspects of what you need. So you need to spend a little more time and look at it a little more thoroughly. So we have screening and then scoring. So this is how screening works. It's like a matrix. So we have rows and then we have columns. And the rows and columns basically capture 2 pieces of information. The first is concept. So we have different concepts, A, B, C, D, E, F, G, are different concepts or models for what we want to make. So these are what are being compared. So it's called concepts. And over here we have criteria. So criteria are things that the product must have or possess to be attractive and to be able to be sold. So we have many functional criteria like ease of handling, ease of use, readability of settings. So these all have to do with the kinds of things that are considered desirable when somebody uses the product. And what we do is we compare these different concepts on each of these criteria. Typically, one of these is chosen as a reference. In this case, D is chosen as a reference, which means it's a baseline. Everything is compared to D. D is not necessarily the best product. It could be arbitrary, or oftentimes it's an industry standard or what you have been making in the past. And the others are new concepts. So everything is compared to D. And they're all given a score of either a plus, a minus, or a 0. A 0 score means it's comparable to D. It's no better, no worse off. A plus means it's better than. And a minus means it's worse than. So, I list all of my criteria and I have all of my concepts and I put in these numbers. The zeros here indicate that A and B in comparison to D are similar. On the ease of use, B has a score of negative. Why does it have a negative score? Well, it's worse than D on this criteria. So that's how we come up with these. And then what we do is after we fill this out, we then add the pluses, minuses, and zeros in each column. So for master cylinder, I have 2 pluses, and that's why I have the 2 here. I have 1, 2, 3, 4, 5. I have 5 zeros, and I have no minuses. So it's a 0. So the net score is a 2 because you got 2 pluses. So it's a 2. The others are zeros. Likewise, if you go to the next column, you got 1, 2, 3, 4 zeros. You got 1 plus and 2 minuses. 2 minuses, 1 plus. So the net is a minus, or rather a -1. So these are your net scores. So when you have your net scores, you compare them. Those products that move on to the next stage are those that have a high positive number, right? Or pretty close there too. -1 won't cut it, so we say no, it's a negative number. -2 doesn't score well, it's not considered. But the first here, it has a score of +2, so that passes the screen. The next one over here, it has a score of +1, that passes. A few others have a score of 0. So when this happens, we know that A passes and E passes, but what about D, F, and G? Well, we look at these. I mean, they don't look particularly bad or particularly good. So in the case of G, we may decide, well, you know, it's got some attractive features. Maybe I can tweak it a little bit, and then the tweaked version, the improved version, goes on to the next stage. D and F individually may have some pluses and minuses. My concept is, what if I combined them and kept the positive and dropped the negative? Maybe they complement one another. So I have a combined concept called DF. So what is screened and makes the screening test is A and E. I'm going to have a G plus, which means an improved form of G, and a new product called DF. It's a combination of D and F. But I've dropped the B and the C because it didn't make it through the screening. Now on the next part, what I do is I go through a process, and this is called scoring. So you will note we kept A, and we have a DF, which is a combination. We have E and a G plus. Now I have to be a little more thorough. I list all of the design criteria, but I'm going to use a scale. I'm still, this time I'm using A as a reference. Now, when I compare with the others, I'm going to use a numerical scale. On this scale, if a particular concept is worse than reference, it's given 1. I'm sorry, if it is much worse, it's given 1. If it is only worse, 2. If it is same as the reference, it's given a score of 3. If it is better than reference, 4. And if it's much better than reference, 5. So as the scores increase, they move in an order of being more and more better than the reference. So we won't be using the plus, minus, and 0, but those numbers 1 through 5. So when you look at this, we are also going to use weights. So when you look at different criteria, right? When you buy a car, you have different criteria. How much does it cost? How safe is it? Does it look pretty? Is the cooling system good? But they're not equally important. Maybe if this is your first job, your number one criteria is how much does it cost? Because you're paying off your college debt and so forth, right? So that would be given a high weight. Whereas how well does it cool? It is important, especially here in Texas. But it's not going to be a number one. So we're going to give weights. So the first one, ease of handling, is given a weight of 5%. The second, ease of use, 15%. It's more important. So I have weights. So what I do next is I come to A, D, F, E, and G plus and give them the ranking. You remember 1 through 5. Now A has a score of 3. DF has a score of 3. Whereas, meaning DF is comparable to A, same as. E and G plus both have a score of 4, meaning they are better than. And so that's how I generate these numbers called the rating. Then I have what is called a weighted score. You get a weighted score by multiplying the percentage weight with the rating. So 5% is how much? 0.05, right? 5% is 5 divided by 100, 0.05. 0.05 times 3 is 0.15. So that's how I get this number here. Look at the next one, it's 15%. 15% is in decimal 0.15. 0.15 times 3 is 0.45. Likewise, I get all these numbers and then I add them up and the net score is 2.75. So I have 2.75, 3.45, 3.1, 3.05. The winner is going to be the largest score. So this is the winner, DF, which has a score of 3.45. The others are dropped. So you see how the Pugh selection matrix is used first to screen from a large number to a manageable 3 or 4, and then we get into the scoring part to help us pick the one final one. But bear in mind, so far we only talked about design criteria here, right? Now, if you want to include environmental considerations also in the decision-making process, we can include, although not shown here, I could include stuff like global warming potential, toxicity, energy efficiency, reuse potential, and then compare each with the other. You know, suppose A is the reference, D would get a score of 4 or 5 if it does much better in global warming potential. You would get a score of 3 if it's the same. You'd get a score of 2 or 1 if it's worse off in global warming potential. So by including consciously in the criteria some environmental performance factors as well, we can make sure the product is not only functional but is also environmentally performing well or is environmentally friendly. So that's Pugh selection matrix.